Alrighty, I wanted to do one example problem of implicit differentiation for you in order to talk about a couple of issues and also to give you a sense of how this looks in the wild. In number 17, we are asked to find the lines that are tangent and normal to the curve at the indicated point. And the equation that they give us, which is an implicitly defined function, is x squared plus xy minus y squared is equal to 1. And the point that we're interested in is the point 2, 3. Now, first of all, a little bit of vocabulary review. Remember that the line tangent is the line whose slope is going to be dy dx. And the line normal is perpendicular to the tangent. And therefore its slope, which I usually denote as dy dx perpendicular, is going to be negative 1 over dy dx, because perpendicular lines have negative reciprocal slopes. So they're really asking us to find dy dx and dy dx perpendicular, and then use those to create the equations of lines. As we saw in class today, because x squared plus xy minus y squared is always equal to 1, we can differentiate both sides of that relation. And when we differentiate both sides of that relation, then we get, on the right-hand side, we get 0. On the left-hand side, we go term at a time. So the derivative with respect to x of x squared is equal to 2x. Here, this is the first issue that I wanted to point out very clearly. We have the product of x times y. So we need to remember to use the product rule. We're going to have first times the derivative of the second plus the second times the derivative of the first. And we clearly need a little more space. And then finally, our third term is simply going to give us the derivative of y squared with respect to x is going to give us 2y times dy dx. Well, let's come now and evaluate the two middle terms here. This is going to give us 2x plus x times dy dx plus y times 1 minus 2y dy dx is equal to 0. Please notice the very real difference between taking the derivative of x with respect to x, giving us 1, and the derivative of y with respect to x, which gives us dy dx. So, in terms of our steps, we've managed to take the derivative of both sides. And now what we're looking for is the value of dy dx at the point 2, 3. There are two ways we could go about it. We could solve for dy dx algebraically and then plug in the 2, 3. Or at this stage, we could plug in the 2, 3 and solve for dy dx. I greatly prefer the latter. Before I go solving, let me plug in to get this down to numeric form. At the point 2, 3, my x value is 2, my y value is 3, and so I'm going to plug in the x and y values. And now this gives me a fairly easy algebraic solve. I have a bunch of terms that are just constants, and I have a bunch of terms that have dy dx in them. And so I can combine those terms to get 4 plus 3 is 7. And I can subtract to get 2 minus 6 dy dx is minus 4 dy dx is equal to 0. Subtracting 7 from both sides and dividing both sides by negative 4, we get dy dx is equal to 7/4. And as soon as we have that, we can now get the equation for the line because we have a point and we have a slope. So I have y minus y1 equals slope times x minus x1, and I'm going to label that clearly as my tangent line. For my normal line, I have exactly the same point, but my slope is the negative reciprocal of the tangent line slope. So there were really two issues that I wanted to bring to your attention here that I want to reiterate now. And the first is, don't forget the product rule. It is very, very easy for students, because they are focusing so hard on implicit differentiation, that when they get to the product right here, they just try to take the derivative of x times the derivative of y and be done. No, never. Always first times the derivative of the second plus the second times the derivative of the first. So that's the first thing. Do not forget the product rule. Second thing is that the right or the most opportune moment to substitute, if you can substitute, is right after you have differentiated. Well, that raises a question. Couldn't I just plug in the x and y first and then take a derivative? Well, unfortunately, that doesn't work. And the reason that doesn't work is that if I plugged in the x and the y, the 2 and the 3 first, then I would just find out that 1 equals 1, which is a true statement, but it does not allow me to compute a rate of change.